picking that up?
Yep.
Good. So this is your syllabus, and right from your syllabus, the first exam ended at basically buoyancy and flotation. So for the second exam, everything from acceleration of fluid masses, probably up to momentum applications is probably how far we'll get. Right now, we're still doing energy considerations, and then we'll have applications for a week. That's what we're kind of in now. Then we'll get to momentum, and that should bring us, momentum actually takes, about 3 classes. So that takes us to almost the week before the exam. So we may get into flow of real fluids before the exam 2, but at this writing, at this juncture, I would say for exam 2, it's going to go from buoyancy and flotation, which are lectures 13 to 14, all the way up to and including lectures 24 to 26, momentum applications. So just expect that on the second exam. So with that, what we can do is start off with going right through your book and right through the syllabus. We can start off on buoyancy and flotation. Basically, that's chapter 3. Then move into acceleration of fluid masses, that's chapter 4. Then into continuity, that's 5. And right now we're on energy. So philosophically, you should be able to do all of the homeworks up through and including lecture 20, which would be chapter 4 and chapter 5 questions. So anything on buoyancy and flotation to start? How many people do we have online?
One person.
So it's Bailey?
Bailey Jones, yep.
Bailey Jones. Since Bailey's the only one online, Bailey, if you have a specific question, you can either unmute yourself and ask me which problem of any of those you'd like to hear, or you can put that in the chat, or if, like many students, you just want to hear me talk and don't have any specific questions, just let me know.
Said chapter 3, question 119.
3119.
Mm-hmm.
So I'm not seeing a 3119.
Oh, oh yeah, 3, okay. Let's see, maybe he means 11.9 or?
So
yeah.
So chapter 3, oh, I do see all these questions, 128, 126. Maybe there's somewhere else in my book. We have, that's the problem. I have the 11th edition. I need to run to my office and get the 12th edition.
Okay.
Or you can read it to me. Let me run to my office and see if I can find the 12th edition.
Okay. He will be back.
recording this?
Yes.
So, I found my book, but I forgot the number under it.
Chapter 3, 119.
119. Thank you.
No problem.
Okay. So. And just make sure your camera captures this. Got me okay?
Yep.
So in this one, we have a sphere, and it's a pressure vessel, and so there's a gas inside of it at an absolute pressure of 10 bar. One bar is atmospheric pressure, so this is under pressure. It has a diameter of 0.6 meters. And the surface ABC, which is this surface, is the interior surface of the left half of the pressure vessel. What is the pressure force acting on surface ABC? So that's the question. So first thing we have to understand is we have a gas in this system. And when we have a gas, again, over a distance, in this case of 0.6 meters, there is very little change in the pressure as you move through the vertical. That's why typically when we have a tank, for example, that's enclosed and under pressure with a surface in it, what we do is if we wanted to find the pressure down below the surface, we wouldn't worry about any of the pressure changes in the gas from where you have the gauge down to the surface, because we would say it's basically the same pressure throughout the gas, because the specific weight of the gas is so small compared to the specific weight of the liquid. So recognizing that, if we cut this system, what we basically have is a pressure distribution everywhere acting on this curved surface of 10 bar. And again, what we would do is, if we're after calculating the force, trying to make sure I'm staying in your
Oh yeah,
field of-
I'll let you know, and I can move it
field of
if
vision.
needed.
Okay,
Yeah.
okay. So for the curved surface, that's our pressure distribution. And again, what we typically do with curved surfaces is divide the resultant force into a horizontal component and a vertical component. So in this case, if we take this hemisphere and project it into a vertical plane, what that looks like is a circle. So again, all you did was take a slice through the sphere, shine a light on it, and this is what you would see projected into a vertical plane. And so basically, our resultant force is equal to the pressure at the center of area times area. That's true for any plane submerged figure. And in this case, that pressure at the center of area is the pressure everywhere, and that's just 10 bar. And that's the area of the circle, pi over 4 times the diameter squared. So again, I just set these up. I don't do all the numbers. I don't know which answer it gives you. You get because it's asking A, B, C, or D. But that's how you would calculate it. And the other thing I might note that this pressure is given in absolute pressure terms. And if the question is asking for the force basically in a gauge pressure datum, what's acting on the other side of the sphere, remember it's just sitting here in air, this is an absolute pressure. So on the other side, what you have is an atmospheric pressure of 1 bar absolute. And so to get the net force in the absolute pressure measurement datum, this would be minus 1 bar absolute pi over 4 d squared. So that's working the whole problem in absolute pressure. If you work the whole problem in gauge pressure, this would have been 9 bar pi over 4 d squared. You get the same answer, but again, this is working the whole problem in absolute pressure, and in that case, you would have to have recognized the fact that you have the atmospheric pressure acting on one side, and on the inside, the pressure of 10 bar absolute. If we work the whole problem in gauge pressure, then you convert both of these pressures to a gauge pressure. An absolute pressure is converted to a gauge pressure by subtracting atmospheric pressure, which is 1 bar. And when you subtract atmospheric pressure from atmospheric pressure, you get 0 gauge. So if Bailey is feverishly writing, if you want to just take a pause after you're writing. If I haven't answered your question, let me know. If I have answered your question, then we can move on to the next one while Ms. Antonellis tells me if there's more than one person online.
2 including me.
2 including you, 3 including me.
Yeah.
So, Bailey, have I answered your question?
He said, that helps me with the question, thank you.
Any other questions, since this is your private review session? Talk about maximizing your tuition benefit.
He said chapter 3, 128.
128. So 128 is a buoyancy problem, and in this case, you have a rod. That means they're not coming in here and putting the juice on the erasers. Let's see if this one works better. They put solvents on these erasers to make them erase better.
Mm-hmm.
So no one's been coming in and putting solvents on erasers. And if we don't do that soon, then it makes it a permanent on the board.
Yeah.
So 3, 128. So you have a uniform diameter rod. And for this uniform diameter rod, it's weighted at the end. So this is the weight end. And that's why it's oriented the way it is. And the liquid A is lighter. Okay. It's weighted at one end and is floating in the liquid, period. The liquid A is lighter than the water, B must be water, or C heavier than water. Show your work. So all you know is this is sitting in some liquid with a specific gravity that's unknown. So we'll call it specific gravity of X. And for this thing, we have dimensions 2L and L. And we're told that the density of the upper portion of this thing, which is height 2L, has the density of water, or W, and the lower portion has a density of 2 times the density of water. So I'm just calling that rho 2, and it's got the density of 2 times the density of water. So again, one of the first things we do in buoyancy problems, just like in fluid statics problems, is to draw a free body diagram. And our free body diagram would be, for example, the weight of the rod that has the density of water. So we'll call that W1. The weight of the rod that has the density of twice that of water. We'll call that W2. And since this is floating, this is counterbalanced by the buoyant force. And remember, the buoyant force is equal to the specific weight of the fluid, which we don't know. That's what you're trying to find, basically, times the volume displaced. And that's equal to the specific gravity of X times the specific weight of water, times again the volume displaced. Okay, so let's just say it does not give you a dimension. It doesn't tell you how deep it's floating. So let's say it's submerged some distance h below whatever that free surface is to where the two different density materials come together. And then obviously the total distance of submergence is L. So in this case, the total draft, if you want to call it, is H plus L. So I'm just throwing that variable in there so that we can calculate some of these things. Ultimately, what we're after is trying to figure out Sx, and if Sx is greater than 1, then the liquid has a specific weight greater than 1. If it's equal to 1, the liquid has a specific weight equal to that of water, and if it's less than 1, the liquid has a specific weight less than that of water. So let me do a little chemistry here. This is the solvent, and it's running out. Another bottle that's almost just as empty. Okay, so now that we have that, I'm going to switch markers to one that hopefully has more juice in it. So we're going to basically solve sum of forces in the Z, positive upwards, is equal to 0. And basically there's only three forces, the buoyant force and the two weights. So in this case, that would say you've got the buoyant force minus W1 minus W2. And contained within that equation is the density or the specific weight or the specific or the gravity or the specific gravity of the fluid. So we'll first put the buoyant force on one side of the equation, and that's equal to the sum of the weights. And the buoyant force is always equal to, again, the weight of the displaced fluid. So in this case, that's equal to the specific gravity of the fluid times the specific weight of water times the volume displaced. And I want to just expand on that term. So that's Sx, gamma of water. And this thing, I don't know if they give us a diameter. Let's see if they do. It doesn't look like they do. So we're just going to say it has some diameter d. And so the volume displaced is pi over 4 times d squared times h plus L. Hopefully all these things I'm assuming, the diameter and h, they're all going to cancel out or at least give me some disposition of Sx. So that's the left-hand side of the equation. And W1 is the density of this material times the entire volume. So remember, it's 2L. So a weight is the specific weight of the material times the volume of the material. So in this case, the material one has the density of, or the specific weight or the specific gravity of water. Material two is twice that. So this is equal to specific weight of water times the height 2L times the area, pi over 4 d squared. That's weight one. Plus weight two is again the volume, which is the end area times the height, L, times the specific weight of the material. And the specific weight of the material, if the density is twice that of water, if I multiply both sides of the equation by the acceleration due to gravity, the specific weight is twice that of water. So that's plus 2 gamma water times the length, because this one is only L in height, times the end area, pi over 4 d squared. And so I think you can see that in all of these terms, that end area is going to cancel. And so the next equation I write, I think I can erase this now. Actually, let's juice this up a little bit. So we're just taking this equation, that equal to that, and we're just getting rid of the areas. So you have Sx, gamma of water, H plus L, equal to gamma of water 2L, plus 2 gamma of water L. And I think you can see the right-hand side basically is the same term, 4 gamma water L. And if we isolate Sx, we're going to divide both sides by the specific weight of water. So the specific weight of water is going to cancel, and we're left with 4L over H plus L. H is less than 2L. So if you remember the problem, the height of the upper half is 2L in height. So H is just an arbitrary value. We don't know exactly what it is, but H would range from 0 to 2L. So we can certainly put in those two limits. And if H is 0, the specific gravity is 4L over L, which is 4. If H is 2L, we have 4L over 2L plus L, which is 4/3. No matter what H is, given the range, the specific gravity is greater than 1. And so your conclusion would be that the density of this fluid is C, heavier than water. So again, I'll give you some time to catch up, and then we'll see if you have something else to add. So, any other questions on this one?
I think he's good with that one. He sent another one that he would like you to go through. Chapter 3, 144.
Okay, 3.144. You have a barge. So I don't believe I went over stability in this course this year, and that's because we missed 3 lectures. So I'm not going to hold this class to stability calculations. So by saying that this will not be on the exam, I can still do the problem for you, or you can just say, okay, then pass, let's go to another problem.
I'll just wait for a response. He said, I'm good to still do the problem. So it sounds like he would like to go through it.
You got it. So, this is 144. So for 3144, they give you this figure of a loaded barge, and what they say is the barge is floating like this, and it's got a side height of 8 feet, and it's got a width of 20 feet in cross section, and you're told that the center of mass is right at the top of the barge, which is not at the water line, it's at the top of the barge. And so into and out of the paper, the ship's length or the barge length is 40 feet. And so given these dimensions, it's loaded with rocks, assume the center of gravity of the rocks is right at the center line of the top surface of the barge. If the rocks in the barge weigh 400,000 pounds, will the barge float upright or tip over? So, again, I didn't go over this in class, but what we have to do is look at what's called the metacentric height. So, again, I didn't go over this in class, but basically this whole system pivots about what's called the metacentric. The metacentric height is this distance gm. And what you're trying to recognize is what you have is the weight acting at the center of mass and the buoyant force acting at the center of buoyancy, which is the center of the volume displaced by the fluid. So those two you can see form a coupled system that could easily result in this ship overturning. And it's not as simple as just looking at those two, but what the derivation does, and this is all actually in your book, you look at the moments about the metacentric height, and then what you calculate is whether this metacentric height is giving you a positive or a negative number. If the metacentric height is a positive number, then the system is stable. It will not turn over. If the metacentric height is a negative number, then the system is unstable. So this distance, and this equation is in your book, the metacentric height is equal to the moment of inertia about the water line. So again, it's the moment of inertia about the water line, divided by the volume displaced, no different than the volume displaced of any floating object, minus the distance between the center of buoyancy and the center of mass. So, in order to get these components, we're looking at first the moment of inertia about the water line. And the water line has dimensions 20 feet by 40 feet. And you already know when we were talking about forces on plane submerged surfaces and trying to find the center of pressure, the moment of inertia of a rectangle is 1/12 the base times the height. And at that point, the question is, well, which is the base and which is the height? Quite honestly, you could do both of them. In this one, that base dimension is going to be the Oh, that's a different problem. No wonder why I'm getting weird answers here. So this would be 1/12 feet h cubed. And in this dimension about the water line, the base is the 40 feet. And the height is the 20 feet. Cubed. And then the volume displaced, we get from the fact that this is a floating system, and that 400,000 pounds is equal to the buoyant force. If this is floating in water, which I assume it is, okay, this is equal to the specific weight of water times the volume displaced, and that volume displaced is equal to the length times the width times the draft, h. So what we would get from this is the draft, and the draft would be equal to the weight divided by the specific weight of water times the length times the width. And again, I didn't calculate any of these, I'm just showing you how you get to the answer. So with that, what we can get is the draft, and with the draft, now we know the volume displaced. That's the denominator over here. And then the last thing is the distance between where the center of mass is and where the center of buoyancy is. So again, what we just calculated was h. And the center of buoyancy is going to occur at h/2. It's the center of the displaced volume of water, which is a uniform media. So for example, if h was 8 feet, oops, let's not make it 8 feet, then we're almost submerged. If h was 6 feet, then h/2 would be 3 feet. And so this g would occur right at the top. h/2 is 3 feet off of the bottom, and if the whole side is 5 feet, 8 minus 3 feet would be a distance of 5 feet here. So again, what you're trying to do is calculate this moment of inertia of a rectangle, volume displaced, and BG is the distance between the center of gravity of the ship and the center of mass of the center of buoyancy of the displaced volume. Each of those is found a different way, although there's a relationship between where you found these two. If you look at the moment of inertia when you switch the axes, you can certainly do that, but 40 cubed is going to give you a much larger moment of inertia about the water lane. So the more conservative approach would be, again, to look at the moment of inertia where this is the height and the base is into and out of the paper. And that's looking at this thing flipping over along this axis. Remember, any barge has 3 axes about it which can rotate. So rotating about the longitudinal axis is rocking back and forth, or you can be plunging into the water. Or if you rotate about the vertical axis, that's called yaw, and that's just meandering through the water. So this equation is giving you the rotation of about the 2 horizontal axes, and one axis is much more stable than the other. Which one would that be where you have a 40-foot cubed? So again, you calculate this. If it's greater than 0, then it's stable. If it's less than 0, it's unstable. Still one person.
Yes.
Okay. Anything else?
Yes. Chapter 4, 41.
So 441 is looking at acceleration of fluid masses, and what you have is an enclosed tank. And in this enclosed tank, you have some liquid, and you have a height, h, and a length, L. And what I'm going to do is, well, I'll get to that. So with this tank, it's accelerated downward at 1.5 g and to the right at 0.9 g. So here's your acceleration field, downward at 1.5 g and to the right at 0.9 g. And H and L are given, so H is 4 feet, L is 3 feet. And the question is, if you have these corners, A, B, and C, compute the quantities PC minus PA and PB minus PA. So, how would we do that? Well, first, let's define a coordinate axis system. And for that coordinate axis system, let's say that this is 0, 0 at A. And if that's the origin, and this is plus Z and plus X, then this would be 0, minus 4 feet. And this one would be minus 3 feet because L is 3 feet, minus 4 feet because H is 4 feet. I just want to check those numbers. Yeah, L is 3 feet, H is 4 feet. So to solve this, again, we're using, because you have an acceleration field, in addition to the acceleration due to gravity, we have to use the relationships we developed for acceleration of finite fluid masses. And what we got from that entire derivation was that dP is equal to minus gamma over g ax dx minus gamma over g az plus g dz. So this is the total change in pressure when moving in the x and z directions under acceleration fields other than gravity. So in this case, as we did in class, we're going to integrate this equation. So we're integrating from, for example, I'll just do one of these. Let's go from A to B. So we're going to integrate this starting at point 1, PA, and ending at point C. And again, gamma over GAX are all constants. So this would be x equal to 0, which is the x coordinate in A, 2x is equal to minus 3 feet when we get down to C. And similarly, we're going to integrate from z is equal to 0 to z is equal to minus 4, which again is the coordinate at point C. And all of these integrations are pretty straightforward. This would be P from PA to PC is equal to minus gamma over GAX. X equals 0 to x equal minus 3 minus gamma over G, AZ plus G. Z equals 0 to Z is equal to minus 4. And I'll do one more step and you should be able to get everything. PC minus PA is equal to minus gamma over G AX minus 3 minus 0 minus gamma over G AZ plus G minus 4 minus 0. So at that point, you should be able to put in the accelerations and calculate pressure differences. Obviously, going from A to B, it's a little bit easier because Z doesn't change. That is, dZ is 0. So you only have that first term. More.
He's saying chapter 5, question 92.
We are just flying through this one. Oh, 5 what?
592.
Okay, water is forced out of this cylinder by the piston. If the piston is driven at a speed of 6 feet per second, what will be the speed of the efflux of the water if D2 is 2 inches and D4 is 2 inches? So 5 and 2. I'll leave that since it's fixed. So, just like a hypodermic needle, you've got a plunger pushing fluid into this system. And again, they give you the two diameters. You have a diameter of 4 inches here and a diameter here of half of that. D2 and D1 is 2 inches. And so the question is, if you know the velocity or the speed of that plunger, what's the exit velocity in this case? And I think this should be pretty straightforward to you. Obviously, if the plunger is moving at 6 foot per second, the fluid right in front of it is moving at 6 foot per second. And so in this case, the discharge is V1D1, V1A1, where A1 is the cross-section area of the 4-inch cross-section. And then again, since there is only one discharge in this system because we don't have a compressible fluid, it's a liquid, that would be equal to V2A2. And again, A2 would be the cross-sectional area of the other one. So again, you just use continuity, and you don't necessarily have to calculate the discharge. All you would have to do is recognize that V2 is equal to V1, D1 squared over D2 squared. Or you can calculate the discharge and then get the velocity. ¿Qué más?
Let's see, waiting to see if he has any more questions.
So ¿qué más, if you say it too quickly, is you burn, or ¿qué más would be anything else. What more?
He says, those are all the questions I had.
Alrighty. My question to you is, what's in store for tonight?
Waiting to hear.
Yeah. I'm thinking I see fluid mechanics in your future. Because you're the only student who showed up, which leaves me a lot of time after this to make up more homework problems. Don't take it personally, I'm just making commentary.
He said, plan for tonight was the rest of the practice problems.
Excellent, excellent. Music to my ears. So I will end this now unless you have more questions. And again, you can always get a hold of me by email, by calling me, or setting up. We can set up a Zoom conference, or just come by my office and we can always talk about questions.
He says, thank you.
Great. So Bailey, go ahead and sign off. I'm just leaving the recording going for like 1 more minute while I erase, just in case other people are watching this and trying to catch up.
Okay.
And once I'm done erasing, you can pull the plug.
Okay, sounds good. Thank you, Dr. Ballestero.
Thank you, Carmen.
Bailey said, have a good weekend.
You too. Okay, that's a wrap.